Today we have Sean, who's now from Berkeley, who's going to tell us about generalized entropy gravitational properties.
Okay, thank you, and thanks for the invitation to speak. I've really enjoyed my time here. It's my first time here at UCLA. So yeah, I'm going to talk about some work that will appear soon, hopefully, with Jeff Pennington and a fantastic graduate student, Gwanda Lin at Berkeley. And yeah, I'm going to talk about generalized entropy. So what's the idea? Well, in the last 20 years or so, we've learned a lot about a deep connection between information theory in CFT and geometry in ADS via the ADS-CFT correspondence. And the typical example of this is this Hubini-Rangamani-Ryu-Takanagi formula, which says that if you compute the entanglement entropy for a subregion in the CFT in some state capital psi, then that should be equal to an area, a codimension 2 surface, that has minimal area. So first you extremize this codimension 2 surface, the area of this codimension 2 surface, then you minimize over all possible extremal surfaces. And the area of that minimal extremal surface divided by 4g is supposed to reproduce the CFT, entanglement entropy. And this is supposed to hold true at leading order in large N, where N is related to the bulk Newton's constant. And we're always going to be working in this talk at infinite 't Hooft coupling. I'll be talking about quantum corrections for this, but it will always be at infinite 't Hooft coupling. Okay, so here's the picture. So here's the boundary subregion B that you define the CFT entanglement entropy on, and here's your extremal surface gamma, codimension 2. So this is a time slice of ADS. Okay, good. And then there were quantum corrections to this formula that were developed by these authors. And they said that if you want to do perturbation theory in 1 over n to find quantum corrections, then what you should do is instead you should find the minimal extremal generalized entropy. So this is now the area plus the bulk entanglement entropy for a field living in this region, which they call a homology surface, which is the region bounded by the boundary subregion B and this surface gamma, this codimension 2 surface gamma in the bulk. So now you're supposed to extremize this generalized entropy, and this is supposed to hold order by order in 1 over n. Okay. And this formula is very interesting. In particular, it gave the unitary page curve for an evaporating black hole in ADS when coupled to a bath. So black holes in ADS don't evaporate because of reflecting boundary conditions. But if you put transparent boundary conditions and you couple to a bath, then you can have it evaporate. And if you do that and you use this quantum extremal surface formula that I wrote on the last slide, then you can get a unitary page curve, which is what people expect for black hole evaporation. So this was a famous result from 2019. And then it was later understood that this formula could be understood in terms of instanton effects in the gravitational path integral. So the page curve is supposed to go up. It's the entropy of the black hole, of the radiation of the black hole. It's supposed to rise and then come back down. And the part where it comes back down is an instanton effect in the gravitational path integral, where a new saddle dominates. And these new saddles are known as replica wormholes. Okay. But there's a lot more to a quantum theory than just instantons. Okay, we should be able to understand gravitational perturbations around a given saddle. This is a big open question that no one seems to have solved yet, but it seems like the natural question. Okay, these instantons are telling us something very interesting. They're giving us unitary black hole evaporation, but how come we can't do perturbations around a given saddle? That seems very weird. And so that's going to be the goal for today. And in particular, we'll see today that in simple settings, these gravitational fluctuations can dominate over regular matter, say. And that is also already an interesting observation. Okay, so one important point is that you can't just treat a graviton as an ordinary massless spin 2 field propagating in ADS because it interacts non-trivially with the area operator, right? So the area is the area in some metric. And the question is it in the background metric? Is it in the metric plus the graviton? What is this area operator and how is it related to the graviton? So that's why gravitons are non-trivial and people had previously been confused by them. Okay, so what's the goal for today? We're going to try to find a prescription for these generalized entropy for gravitons. And it's going to satisfy 3 requirements. First, it's going to be gauge invariant with respect to perturbative diffs. That's key. Second, we want to take the form of area plus a bulk entanglement, like the formula I wrote on the first slide. This generalized entropy, we want it to be an area plus bulk entanglement. And the third requirement is we wanted to agree with the CFT. So we had this formula that generalized entropy in the bulk was equal to CFT entanglement entropy. We want that to always be true for our formula. And the way we're going to do this is we're going to have an explicit example where we can just check both sides. And we'll see that it agrees with the CFT. Okay, so what are the difficulties? Well, First, you have to figure out which entangling surface. What are we extremizing? How do we find this codimension 2 surface gamma? And what's the area operator? So this is something that I mentioned before, but you want to figure out what is the area operator of, in what metric, what surface, and so on. And you want to make this thing gauge invariant. That's very important. And you want to figure out how to compute entanglement entropy for gravitons. So this is an old problem because in gauge theories, you don't really have factorization of the Hilbert space. So if you wanted to find entanglement for some subregion, the constraints of the gauge theory relate that subregion to its complement, and it's non-trivial in order to factorize that Hilbert space and actually define an entanglement entropy. So I'll touch on that mostly at the end. Okay, so usually the way we learn these rules, we want to compute generalized entropy and relate it to CFT entanglement, is we use the gravitational replica trick, which was taught to us by Lukowitz and Naldacena, and then quantum corrections were developed by Faulkner, Lukowitz, and Naldacena. And basically, you do replica trick on the boundary to compute entanglement entropy, and then there's a corresponding bulk replica trick, and that teaches you the rules of how to compute this. But there's a problem, which is if you have gravitons, the spacetimes on which you compute this generalized entropy is actually off-shell when you compute the matter entropy, and it's very confusing how to put gravitons on an off-shell background. So people didn't really know how to do this, and it's still an open problem of how to actually derive these things from the path integral. So instead, what we're going to do today is we're just going to do a direct Hilbert space calculation of everything. So we're not going to have any path integrals today. Everything will just be Hilbert space calculations of entropies, areas, and so on. And we'll see how to get a match. Let me say that these three requirements that I had on the first slide, that it be gauge invariant, that it agree with the CFT, and that it be areas plus bulk entanglement, that turns out to be non-trivial. It's actually like pretty easy to find things that satisfy two of those three, and the crux of today is going to be one that satisfies all three of those requirements. And this Hilbert space calculation will allow us to check that it does that. Okay, so that's the introduction. Maybe I should pause here. Any questions about the basic goal? Okay.
I'm sorry, the fact that it had to be area plus something, is that not up for your obvious, right? Because there's other things, so that's there's any other justification for that or motivation for that?
No, it's just a nice formula because that's what's true for regular matter. In fact, you can write down formulas that don't take that form, and we derive those first. And then we got confused and said, okay, why is it not an area? And it turns out there is a way to write it in terms of areas.
But is each term in the sum well defined under gauge transfer gauge?
Yeah, the area will be gauge invariant and the entropy will be gauge invariant separately. Yeah. Okay, so let me first tell you about the prescription. But first, let me tell you how you would do this for regular matter, because maybe people in the audience aren't familiar, how you compute this generalized entropy for ordinary matter. So what do? You consider some quantum field theory in ADS, in some state psi, and you expand around a background. So capital G here is the background metric. It's asymptotically ADS, and then you have some backreacted metric G2, and you solve Einstein's equations semi-classically in this state psi to backreact the matter on the metric and solve for this G2. This is the backreacted metric. Okay, and once you have the backreacted metric, you compute the entanglement entropy across the classical surface, and you put all these together. So you have the area in this backreacted metric of the classical extremal surface plus this entropy of the bulk quantum fields across this classical extremal surface. Notice that there's no change in the surface because the surface is classically extremal. So perturbations to this surface would be a higher order effect in G Newton. So they don't appear at order here, which is order n to the 0, or in the bulk it's order G Newton to the 0. So yeah, that's why there's no perturbation to the surface here in this formula. Okay, and this formula has experienced many checks, and I think it's widely believed to be true for ordinary matter that are not gravitons. Going to higher orders in G Newton is a subtle thing. I'm not going to talk about that at all today. But at least to order G Newton to the 0, this formula is widely believed to be true. Okay. So what's the setup for today? I'm going to consider expanding around an asymptotically ADS background, which is again this capital G. Then I have my graviton H and my backreacted metric G2. And kappa here is square root G Newton. So this is the correct coupling constant if you want the graviton kinetic term to be canonically normalized. We'll see that in a second. Yeah, so here's the graviton action. the free graviton action. So we're dropping all interaction terms that come from expanding Einstein-Hilbert action. Here's just the free graviton, and here it's on shell. So I put the background on shell explicitly. Here's the free action, and the covariant derivative is always the background one. Okay, and now we need to talk about diffeomorphisms. So what do we mean by diffeomorphisms? There's two types. So there's background diffeomorphisms. These are the ones which I call epsilon zero. So they act on the full metric little g like this, and this transforms the background metric capital G in the usual way under diffs. These we're going to fix. So we're going to pick some background diffs, which will be some nice choice of coordinates for our background. And they transform waves in some weird way that's not important. But then there's perturbative diffeomorphism, which I call epsilon 1. These are proportional to kappa. These fix the background, but they change the graviton in the usual way under diffs. So these are the ones we're going to really care about, is gauge invariance with respect to these perturbative diffs. And then there's obviously order kappa squared things here, which affect G2, and I'm ignoring those. That's not really important, actually, for what I'm going to say. Okay. Good, so that's the setup, just free gravitons propagating on ADS that back react on the spacetime. So before we study the full quantum problem, which is hard, let's just say, what can we learn from classical phase space? So I'm not going to quantize anything yet. Just treat this metric classically and see what classical phase space can teach us. So Hollins and Wald studied this problem. They studied covariant phase space for gravitational perturbations around stationary black holes in asymptotically flat spacetimes. And you can generalize that to asymptotically ADS, which is what we need for today. And they chose a particular gauge to do their analysis. So what is the gauge? You take the classical bifurcation surface, which I've been calling the extremal surface. These are the same thing for spacetimes with a bifurcate killing horizon. So you take the bifurcation surface gamma 0, which is the extremal surface. And here extremality can be characterized by the fact that this surface has two normal vectors. Those two normal vectors define two extrinsic curvatures. And the condition that this surface gamma 0 be extremal is the condition that the trace of those extrinsic curvatures vanish. That's this condition. And the choice of diffeomorphisms that Hollins and Wald made was a choice where you take your perturbed surface, say you solve for the surface in G plus kappa H, you find some new extremal surface, and you take a diff that moves it back to the old surface. So that's the condition that the extrinsic curvature, even in this metric G plus H, is still 0 at the old surface. So you've just mapped your new extremal surface back to the old one. That's this Hollins-Wald condition. That was their gauge choice. And then there's a secondary gauge choice, some residual gauge symmetry, which is that this stationary spacetime has a killing vector. And you choose the gauge such that it's still a killing vector on the classical extremal surface. This one is not really that important, but it's useful for their analysis. Okay. So from their analysis, what did they derive? They derive some relationship between boundary charges and bulk charges. So on the left-hand side here, I have the boundary charges. So in ADS, these would be the CFT charges. And in the bulk, these are related to some areas. So here's HW means Hollins-Wald gauge. This formula is only true in Hollins-Wald gauge. Here's the linearized area of H in their gauge on the classical extremal surface. Here's the back-reacted metric, still linear in the back-reacted metric, and then quadratic in H. So the area is some nonlinear function of the metric. So you get quadratic terms in the perturbation. That's this. So this is the leading term in kappa. This is 1 over kappa because it's just linear in H. And these are the kappa to the 0 terms. And then there's some canonical energy term, which is kind of a funny term that we have to deal with. So you can think of it as the boost energy. So this killing vector generates some symmetry in the spacetime, and you can think of it as the energy with respect to that. So it's defined like this. Omega is the symplectic form for the gravitational phase space, and it's just some integral of that symplectic form on the Cauchy slice sigma of the graviton and the leader with respect to that killing vector of the graviton. So you can think of it the energy with respect to that killing vector. So in Rindler, it would be the boost. And S here is just some surface gravity. Okay, but it's not really, this thing is actually a funny object. So I said it's kind of like the boost energy, but it's actually not gauge invariant in an important way. So Yeah, so this whole thing is not gauge invariant. These areas are not gauge invariant. They're defined in some specific gauge. And this economical is also not manifestly gauge invariant. Okay, so how do we make this thing gauge invariant? First, to make the area gauge invariant, it's actually pretty simple. You just don't do the thing where you perturb the surface back. Just keep the original gamma 1. So you find some new extremal surface gamma 1, which is your perturbed extremal surface. Solve for that by setting the extrinsic curvatures to 0, and you get some perturbed surface. And so now compute the area of this thing, perturbatively in kappa. So that's the way to make the area gauge invariant, because extremal surfaces are always gauge invariant. Okay, this ecanonical thing is not gauge invariant. In particular, if I do a diffeomorphism from Collins wall gauge to any other gauge H, you pick up this boundary term, you see? So the ecanonical in H is not equal to ecanonical in H Collins walled. But this now makes the left-hand side gauge invariant in the following sense. The left-hand side is just some number, it's some energy. And in any gauge, I compute the right-hand side, and I get this number, which is the left-hand side. So ecanonical is not gauge invariant, but ecanonical plus this boundary term is gauge invariant. It just computes this number in any gauge H. Okay, so here's the full gauge invariant version of what Collins-Wald did. Okay, so that's what we can learn from phase space. And why do we care about any of these formulas? Yeah.
Like what is the transformation that is generating the new surface? So gamma. So
Find gamma 1?
yeah. So
Yeah. So you take the extrinsic curvatures of a codimension 2 surface, but this delta means that it's with respect to H. It's the extrinsic curvature in the metric H, not in the metric capital G. And I solve for extrinsic curvature being 0 for H. And that finds a new surface for me in the space-time. So I have my original surface gamma 0, which is the classical one with respect to capital G. And then H will find some new surface, perturbatively away from the old one. And that's how I find this gamma 1. Yeah, in fact, I'll have plots of gamma 1 later in the talk. You'll be able to see what it looks like. Okay. Okay, so why do we care about any of this classical phase space business? Well, in state psi and spatial subregions B in the CFT, where the modular Hamiltonian K psi B, which is defined down here, minus log of the density matrix, for those particular states and subregions where the modular Hamiltonian generates an asymptotic killing vector. So I said there was a killing vector in the bulk, you take it to the boundary, generates an asymptotic killing vector. When that's true, here's two examples. You take the thermal state in the CFT and the entire spatial slice, or you take the vacuum state in the CFT and you take a polar cap subregion of the sphere on a t equals 0 slice of the cylinder. These are both examples of such states and regions. Then this boundary charge that I wrote down on the left-hand side of the Collins-Wald formula is just this modular Hamiltonian, KB psi, which is minus log of rho psi, which is part of what appears in entanglement entropy. Right? Von Neumann entropy is minus the trace of rho log rho. So this is like a piece of the von Neumann entropy. And similarly in the bulk, this ecanonical Collins-Wald is actually the bulk modular Hamiltonian for the dual state psi in the bulk. Okay, and for perturbations around a state, so I have capital phi is a perturbation around the background state psi. For those, the change in the entanglement entropy, so I take the difference between the entanglement entropy in the state phi and psi. To leading order, that's just the change in this modular Hamiltonian that I wrote here. So the left-hand side of that Collins-Wald formula is like the leading order contribution to von Neumann entropy perturbatively around some background state psi, when psi has these properties. So it's giving us like a clue of where to look to get the generalized entropy. And similarly for the bulk state. So I could have also done little phi and little psi, and this formula would also be good. So the bulk entropy will also have a formula like this. Okay, good. So that's what we're going to learn from classical phase space, and that's going to motivate us where to look of how to get our formula for gravitas. But now we're going to go to the quantum problem, and we're going to say it's actually more non-trivial because you can't just directly naively quantize that classical phase space for reasons we're about to see. So suppose we just try to quantize the area. So you take the area of Collins-Wald, you try to put it to an operator by replacing H to H hat. And then normal order quadratic operators in H. Okay, realize you immediately have a problem, which is if you try to extremize this thing, it's just zero for say single particle states of the graviton in the bulk. So you would never find a new extremal surface because this would just give you zero. So you would never find a gamma 1. So that's just not gauge invariant. Okay, so this is just bad. You can't just naively promote H hat to an operator. What you can do instead is, so here's the graviton canonically quantized. So I've written as a sum of our quantum numbers little q. Here's the gravitational waves. And here's my my annihilation operator, where H here is the gravitational wave that solves the linearized Einstein equations. Now I construct a Hermitian a Hermitian surface operator out of these A's and A daggers. And here gamma is just some arbitrary codimension 2 surface that's anchored on the boundary of my boundary subregion B. And then I extremize this object. So it's the graviton and the surface operator. And then similarly here you have the surface operator squared, and you normal order everything. That's what these dots mean. And you extremize that thing. That will be gauge invariant. And in particular, it would give you the same thing as if you were to just classically extremize the area. So in this metric H, if you were to extremize the area, you would get the same result for this trace, classically. Okay, so then you say, well, why treat the area term classically at all? Why not just treat the area term classically? Why are you treating it quantumly at all if the thing you just wrote down is going to reproduce the classical area? Okay. The problem is that this would not be consistent with the CFT. You actually can't treat the area term classically. And why is that? So consistency with the CFT at order 1 over kappa requires the following property, that for single particle states, the 1 over kappa contribution actually vanishes for the classical extremal surface, but for superposition states, it doesn't vanish. And in particular, it gives a 1 over kappa generalized entropy. So this we can just check explicitly in the example that I'll give later in the talk. Okay, so you have to treat the area as an operator, and you have to treat gamma as an operator in order for gauge invariance and consistency with the CFT. Okay, and the last thing we need is the relative entropy. So I said that delta S, the difference of entanglement entropies, was like delta K, but it's not delta K. There were these corrections, these order rho squared corrections. And these order rho squared corrections come from the relative entropy, which is defined like this. So rho 1 is some density matrix, rho 2 is some density matrix, K2 is the modular Hamiltonian for rho 2, K1 is the modular Hamiltonian for rho 1. And this is the relative entropy. Okay, and I claim that the relative entropy in the bulk is equal to the relative entropy in the boundary. So why do I say that? Well, it's true for ordinary matter fields. This was proven by Jafferis, Lukowitz, Malgasena, and Su in 2015. And it's also an important property for the duality between boundary subregions and bulk subregions. So there's something called entanglement wedge reconstruction, where a boundary domain of dependence for a subregion is dual to a bulk domain of dependence bounded by the classical extremal surface, gamma 0. And in order for that duality to actually hold, you need distinguishability of boundary states in that subregion to be the same as distinguishability of bulk states in that subregion. And relative entropy is a measure of that distinguishability. So this equality is important for saying that if you can distinguish states in your boundary subregion, you can distinguish them in your dual bulk subregion. Okay. And the final reason is that I'm going to just show it in a specific example for gravitons, that this is true. And I think that it's true for any state in the graviton Hilbert space. I'll show it for one of them, but I think the argument holds for any of them. Okay. So now putting this all together, we showed that the leading order to delta S was delta K, and so the relative entropy gives the correction to that perturbative formula. So once you have that the relative entropy is the same, and delta K is related by Holland's wall to delta K in the bulk, then you can construct the generalized entropy formula. Okay, so here's our prescription. Treat the back-reacted metric as an operator on the graviton Hilbert space that you solve by solving the linearized Einstein equations for G2 sourced by the quadratic Einstein tensor for H. Okay, then you compute the trace of the following area operator. So here you have, again, G2 is now an operator. You compute this area operator. compute, and this piece gives the bulk entanglement entropy. So compute the trace of this whole thing, extremize it over gamma hat to find a new extremal surface operator, gamma hat psi. And my claim is that if you do that, then the following formula holds for any state in the perturbative graviton Hilbert space. That the entanglement entropy difference between any excited state and the vacuum is equal to the generalized in the bulk for any excited state in the vacuum. And this is only, I think it's only true to order kappa to the 0. I don't have anything to say about higher orders. And you might be asking, why didn't I say anything about S? So here I wrote a formula for delta S. The reason is twofold. One is I don't know actually how to compute S, and we can't use the path integral, so I can't make any claims about the entropy itself. I can only make claims about the change in entropies. And we'll see in the example that I'll give why I can't compute entropies. But this is the only thing I know how to compute, so this is the only thing I can claim. The other reason is that entropy is actually very subtle for these reasons that I discussed previously, that diffeomorphism invariance puts some constraints on the Hilbert space, and you have to deal with that constraint. And actually this delta S, you don't have to deal with that constraint. I'll explain that at the end of the talk. So this delta S is much nicer than S itself. And that's why I only have a formula here for delta S. Okay, good. So that's our prescription. What are the takeaways? It satisfies these 3 requirements that we want. It's gauge invariant, it's an area plus a bulk entanglement, and it agrees with the CFT, which will be the second half of the talk. And the area operator is well defined, it's gauge invariant, all of the things that we would like. And it has the interesting property that different states pick out different extremal surfaces. So these new extremal surfaces, gamma 1, are state dependent. And there was this large class, these superposition states, that have the property that they have parametrically larger generalized entropy than ordinary matter. They have this 1 over kappa generalized entropy, so larger than any ordinary matter field. Yeah, so that's this statement. Delta S gen for those superposition states will have this 1 over kappa. In fact, it's any state for which the graviton has a non-zero expectation value. Okay, good. Were there any questions about the prescription? Now I'm going to give you an explicit example where I can prove this explicitly. Okay. So how do we actually compute these things? So here I'm going to consider a general d-dimensional CFT in d greater than 2 dimensions. It's going to live on the cylinder, and it's going to satisfy these 2 requirements. So CT here is the coefficient of the stress tensor 2-point function. It roughly measures the number of degrees of freedom in the CFT. I want that thing to be very large, parametrically large. And this thing is, okay. So I want this thing to be parametrically large, and I also want it to be much larger than delta gap, where delta gap is the conformal dimension of the lightest single trace primary operator with dimension j greater than 2. So spin j greater than 2. That's my definition of delta gap. And the CT is roughly like G Newton, or rather 1 over G Newton. It's n to some positive power in holographic CFTs. So it's 1 over G Newton, so large n is small G Newton. Okay. And Heemskerk, Penedenis, Polchinski, and Sully in 2009 showed that these are necessary conditions for the CFT to be dual to a weakly coupled Einstein gravity in ADS. So these are important conditions for actually getting an entanglement entropy on the CFT that will give the correct generalized entropy in the bulk. Now I'm going to consider an excited primary state. So take the stress tensor, which is the boundary dual of the graviton in the bulk, and act it on the bottom of the cylinder. And epsilon here is just some polarization tensor. And the subregion I'm going to consider is some polar cap at the t equals 0 slice. So I have a sphere at t equals 0, and I take some polar cap subregion with some angular size theta naught. Okay, so now we need to construct the reduced density matrix. To do that, we're going to use this Cassini-Huerta-Myers map, where you map this subregion on the cylinder to all of hyperbolic space times a circle. And this subregion is mapped to the tau equals 0 part of the circle and all of hyperbolic space. And this has the nice property that under this map, the vacuum density matrix defined in the subregion B gets mapped to the thermal density matrix. on this hyperbolic space. And the excited state gets mapped to this TT product. Okay, so now we can actually compute this modular Hamiltonian, which we need to compute the von Neumann entropy. So we're going to expand around the vacuum. So this excited state density matrix is the vacuum density matrix plus some perturbation. And the modular Hamiltonian, as I said, is minus log of the density matrix. So write the log as some integral representation. And then that integral representation can be expanded like this. So the leading term is the vacuum modular Hamiltonian plus an infinite set of corrections to the vacuum modular Hamiltonian. And these are known explicitly. So here's the explicit form of delta K. It's delta rho, this perturbation of the density matrix, flowed in time by the Hamiltonian hyperbolic space, infinitely flowed, the average over all flows in time of this delta rho, and you take n products of that flow. And they're situated around the circle. Okay, good. And the kernel is known. So there's some kernel here when you do the integral over all flows, and that kernel has some explicitly known form, which is this, worked out by these authors, Sarosi and Bugushin. Okay, so we have an explicit formula, and at small theta naught, this delta rho is small. So that's going to be the key. We don't have to do this full infinite sum over n. When theta naught is small, delta rho is small, and you can truncate this sum to just the first few orders in n, first few n values. So that's what we're going to do. So now let's compute the von Neumann entropy. So here's the vacuum subtracted von Neumann entropy. It's trace of rho times the modular Hamiltonian for the state T minus the vacuum density matrix times the vacuum modular Hamiltonian. And it's just given by this infinite sum again, and the vacuum subtracted vacuum modular Hamiltonian. This first term is what's known as the first law of entanglement, that at leading order, delta S is just delta of the vacuum modular Hamiltonian. And that thing, for the particular case we're considering, is actually a local operator. It's an integral stress tensor. Here I've written it on the cylinder, not on hyperbolic space. So it's the stress tensor times some kernel integrated over the subregion. So the subregion is theta goes from 0 to theta naught. This is the vacuum modular Hamiltonian. And when you do this, this vacuum subtracted expectation value is a stress tensor 3-point function. And the stress tensor 3-point function in CFTs is fixed up to two constants, theory-dependent constants. It's fixed by conformal symmetry and conservation of the stress tensor. And this is why we need these assumptions. So the assumptions I made at the beginning on the CFT, that CT was much larger than delta gap was much larger than 1. That condition was shown in a beautiful paper by these authors to completely fix the stress tensor 3-point function to be that given by the Einstein gravity 3-point vortex. So once you have that result, then you know what the 3-point function is and you can do the integrals. And here's the result. Okay, it's not important what it looks like, it's just some complicated thing that we're going to have to match in ADS. And I picked some particular polarization tensor here that is the one that corresponds to the state in ADS for the graviton that we're going to consider. Then the first subleading correction is a 4-point function of the stress tensor. And here it's integrated, and you can compute it by using large N factorization. So at large N, 4-point functions factorize into a product of 2-point functions. And then you do the integral over all of these flows in time, times that kernel that I wrote down on the last slide, and you get some explicit result, the second order correction. So this is the minus the relative entropy in the CFT. Okay, good. So that's the CFT calculation. Now let's do the bulk calculation. So here's global ADS in d+1 dimensions. And I'm going to start with the full unconstrained phase space of my gravitational wave and its conjugate momenta. And I'm going to pick a particular gauge. I'm going to choose radial gauge. This just turns out to be a simple gauge to choose. And then I'm going to impose diffeomorphism constraints, which gives some reduced phase space, plus this gauge condition. And then with this reduced phase space, you have a Dirac bracket, and you use Dirac quantization to quantize this theory. So Dirac taught us how to quantize gauge theories. You take this Dirac bracket, you promote it to a commutator, and that gives you the quantum theory on this phase space. Now we need to go and find this graviton. We need to actually solve for this gravitational wave. So the way you do this is that ADS has T and R component, and then it has some SD minus 1 here. And on the SD minus 1, the graviton decomposes into a scalar, vector, and tensor part, and these all decouple. And so then the graviton operator is a sum over the different parts. So it's the usual sum over quantum numbers, but also a sum over these scalar, vector, and tensor parts. Okay, and there's also an extrapolate dictionary which relates the bulk graviton to the boundary stress tensor. They're related in this way. You take the limit as you go to the boundary, r goes to infinity, of some power of r times the graviton operator. That gives you the CFT stress tensor, up to some proportionality. Okay, and the state we want to consider, I'm going to consider the lowest energy mode of this scalar part of the graviton. This corresponds to the state I considered in the CFT. T dotted with the special polarization. And it turns out you can actually analytically solve for this gravitational wave, this lowest energy gravitational wave, which is kind of remarkable, but it's actually possible in this gauge. Good, so now you have this, you have the state you want, and you have its wave function. Now you can just go solve for the area contribution. So we had this boundary subregion B, which was some polar cap. And the classical extremal surface there will just be the bifurcation surface for a Rindler wedge in ADS. So gamma 0 is just the bifurcation surface. And okay, so here I've drawn it. So here is B, our boundary subregion. I've drawn a partial spatial slice. So there's, this is really a full circle, and I've just drawn part of the full circle. Here, the light blue is the boundary subregion. Here, gamma 0 is the bifurcation surface of Rindler. And here, this magenta is the new surface gamma 1. So we extremize this area operator with in that particular state, with that particular wave function, and we get some new surface. And notice it has some non-trivial time dependence. It dips down in time. And then you can actually analytically solve for the back reaction in that state. And putting that all together, you get the area contribution. Okay, so it turns out here I've written in d equals 4. You can do it in any dimension. You can extract explicitly the area contribution from this graviton. It's again some complicated thing that you need to match the CFT. And here I've written it order by order in theta naught. So in principle, we can't solve it at finite theta naught, but order by order in theta naught, you can compute it to any order and then match the CFT. Okay, good. So now we want to go, so the final part is we want to compute the graviton entanglement in the bulk. That will be the final step, and then we'll get our generalized entropy. So what do we want? So here I've actually plotted the T theta component of this gravitational wave. These sort of kinks here are just because I plotted the magnitude. So it's some lump of matter sitting in ADS. Here's my boundary subregion. Gamma 0 here is my Rindler bifurcation surface. And here's my homology surface, sigma b, which I'm going to also sometimes call the right wedge. And here's the complement, the left wedge. So I have some lump of matter, which is my excited state. I want to trace out the left and compute the von Neumann entropy for the right. That's going to be the goal. So we need our excited state density matrix. So we start with Rindler. So Rindler can be written as the following entangled sum of energy eigenstates on the left and on the right. So here there's a product over all the different scalar vector tensor modes. H here is because we're in Rindler. So these label the Rindler decomposition, as you'll see in a second. We're only going to care about the scalar one. And here I've put in some UV cutoff. So the Hilbert space in QFT never really factorizes. You have to put in some cutoff and then define this factorization. Okay. And here's the vacuum. It's just the thermal density matrix for Rindler. And so the vacuum modular Hamiltonian is just the Rindler Hamiltonian. It's given by a sum of omega times b dagger b, where omega is the Rindler frequencies. Okay, so, and there's a sum over, again, the scalar vector tensor modes. Sorry, did I miss a slide on quantization of the, no, okay, it's coming next. Quantization of the graviton and Rindler. Okay, so we want to we want to trace out the left. So the way we do this is we write everything acting on the left in terms of things acting on the right. Sorry, I think there is something missing with the Rindler quantization. Okay, well, let's keep going and I'll explain it later. So the good. So quantities acting on the left can be rewritten as quantities acting on the right. So these Bogolyubov coefficients, these relate the global creation annihilation operators to the Rindler annihilation and creation operators. So the A dagger for the global Hilbert space can be related to the Rindler modes B dagger by these Bogolyubov coefficients alpha and beta. And it turns out that you only need the scalar mode of the Rindler Hilbert space. So these are the Bogolyubov coefficients relating the scalar global mode to the scalar Rindler mode. And you can rewrite all of the ones on the left in terms of acting on the right, and similarly, the annihilation creation operators acting on the left in terms of annihilation creation operators acting on the right. Once you've done this, you've traced out, you've removed all left quantities in terms of right quantities. Now you can trace out the left. So here's the reduced density matrix for the excited state. It's written in terms of these Bogolyubov coefficients relating the global and Rindler modes and the annihilation and creation operators for Rindler. And then here's the vacuum modular Hamiltonian for Rindler. Okay, so you have some explicit density matrix for the excited state. Okay, and now you can go compute the entanglement entropy. So to compute this, we're going to use the replica trick, but not the usual replica trick where you have a replicated manifold. This is just Hilbert space calculation of entanglement. So you just have n copies of your density matrix, rho psi. You take a derivative with respect to n and set n equal to 1. So you have to actually analytically continue this trace rho to the n. So how do you do this? Again, we expand at small theta naught, some perturbation of the density matrix around the vacuum. And when you do this, the replica trick, at leading order, you just have, again, the first law of entanglement. That gives the following integral of these Bogolyubov coefficients, which you can compute analytically and in a gauge invariant way, which means that this vacuum subtracted von Neumann entropy will be gauge invariant. Because these Bogolyubov coefficients can be manifestly computed in a gauge invariant way. And this is the result you get. Okay, and then you can do the same thing at subleading order. It's more complicated. You get the following result. You get the trace of the excited state density matrix times the vacuum times this object here. So look at this object. It's some sum of the excited state density matrix conjugated by the vacuum to some power. You have to compute this sum, analytically continue in n. Take a derivative and set n to 1. That gives you this middle object. And this gives you the final contribution. And you'll recognize that this is exactly the CFT relative entropy minus the CFT relative entropy. Okay, so we got an exact match. In particular, if you add this to the area contribution, you get an exact match with the CFT. So our prescription is good, and we can explicitly check it in this example. Now, there's something that I kind of swept under the rug here when I did this calculation in Rindler, which is I didn't talk about this problem of constraints. The fact that the graviton Hilbert space doesn't factorize even with a cutoff because there's diffeomorphism constraints which relate the Rindler subregion to the complement Rindler subregion. And the reason is they don't actually really matter. So maybe I don't know how much time I want to spend on this because it doesn't really matter, but let me briefly explain what happens. So if you have a gauge symmetry, then the Hilbert space isn't factorized because there are constraints. So in Maxwell theory, the Gauss law relates the perpendicular component of the electric field on one side of the entangling surface to the perpendicular component of the electric field on the other side in this way. So this is some constraint on the Hilbert space. Psi physical is a physical state on the global Hilbert space, and written in terms of the states in A and the states in A complement, it has to satisfy this requirement. Okay, and similarly for gravitons, there's d+1 constraints in d+1 dimensions coming from diffeomorphisms. So here HI are the charges for diffeomorphisms. So usually to restore factorization, what you do is you fix the boundary value of the charge, and then you sum over all super selection sectors corresponding to the different values of that boundary charge. And you impose that the boundary charges agree on the two sides of the entangling surface. So in particular, the density matrix will be here's the sum over super selection sectors, weighted by the probability of being in a super selection sector. Here, Qi is the eigenvalue of this charge Hi. So you sum over all those eigenvalues, labeling your different charges. And here you have the density matrix on A and the density matrix on A complement. And you require that the charges agree. So here Qi for A complement is the same as Qi for A. So here you have a sum over super selection sectors. This thing satisfies the constraints and it now factorizes. And when you do this, you get two contributions to the entropy. Sorry, here there should be an A on all of these density matrices. These are the reduced density matrices for A. When you do that, you get the von Neumann entropy as a bulk piece coming from these density matrices, plus some edge piece coming from the Shannon entropy of these probabilities. And it turns out, I claim that you don't need these. So this S edge actually doesn't contribute to delta S. So Gwanda and I showed this earlier this year in a paper for photons. We showed explicitly by calculation that for any finite energy states above the vacuum, this delta S doesn't contribute. And I think it's also true for gravitons. The other piece of evidence is I just showed you that our formula for generalized entropy gives the CFT entanglement without any edge contribution. So that's why I think that these are not important. That's one of the nice features of computing this delta S rather than S. Okay, good. So let me end with open questions. So the biggest open question is how do you derive this from the gravitational path integral? So here I just did a Hilbert space calculation. And the really thing we would like to have is the gravitational path integral. In particular, I gave this prescription where you promote the surface, the codimension surface to an operator and extremize that and then compute the trace. But you could have done something else. You could have just treated H and the surface classically, extremize that, then promote them to an operator and compute a trace. Okay, that's less natural, but at this level, you can't distinguish them. And maybe the gravitational path integral can distinguish those two prescriptions. I gave the more natural one, but maybe from the path integral perspective, it's not more natural. There's this problem with gravitons propagating on off-shell backgrounds that is hard to deal with and people haven't really solved. So Andreas Blomart and I gave a prescription earlier this year for how to deal with it, but it's not a priori clear that we did the right thing. There's another thing, which is when you do this replica trick for gravity, you really have there's some replicated manifold that fills in the replicated boundary, and then there's some quotient manifold because this replicated manifold has some replica symmetry. There's a Zn symmetry, and when you quotient by that, you get some replicated manifold, and the gravitons actually live on this replicated manifold. And so you need to figure out how to relate diffeomorphisms on that replicated manifold to this quotient space. Okay, that's a technical issue, but it's an important one. And what is the area operator from this perspective? How does it show up in the gravitational path integral? I think this is another important question. Here, I've really just been talking about perturbations around a classical extremal surface, but I motivated the whole talk by talking about these replica wormholes and this unitary page curve. And those come from a non-trivial quantum extremal surface known as islands. And here, I don't know actually how to deal with gravitons on those, around those extremal surfaces. In particular, now the matter entropy has large gradients, and it's actually non-trivial. We don't know yet how to prescribe a formula for these kinds of situations. Okay, and the last thing, which I think is really important, is why do we care about gravitons? Well, we want to know if this quantum extremal surface formula is really a quantum gravity formula, or if it's just a formula about QFT and curved spacetime. And I think that's the most important question to ask regarding this formula. And I think this graviton formula is telling you, okay, perturbatively, it seems to make sense around classical extremal surfaces. But we want to know, is it really a quantum gravity formula? The fact that it gives a unitary page curve seems to say yes, but we don't know. And I think to really answer this, you need to embed it into string theory. So here I've just been doing low energy effective field theory in ADS, but we know that ADS CFT is really about non-perturbative strings. And so we could ask, can you embed this whole story into perturbative string theory? And then you could really maybe say whether or not this formula makes sense in full quantum gravity. Okay, thanks.
Actually, in the last part, when you mean string theory, you just. I mean, you're just free gravitons here, so we just did. Free modes of the string, would it really change anything much?
Yeah.
Or is it you're talking about a question of actually including interactions?
I don't know what happens if, I think both are interesting. I don't know what happens if you include all the higher derivative terms in the action. So you have to include all of the higher derivative terms that you get from string theory and resum them. I don't know what you would get for the formula. If it would still be area plus bulk entanglement. I mean, it's not area because it's this Dong entropy, but I don't know what happens if you resum all of it.
Even for the, if you just have the quadratic part, can you just transform it? Can you just,
I think,
transform that to canonical quadratic?
yeah, I think yeah, so the if you take like r squared, r cubed, and so on, you can use this Dong entropy, and I think all of this would still work. But I think if you had all of the higher derivative corrections, I don't know. Yeah. I mean, as well, one would like to include interactions. I think, yeah. Here I've just been doing free gravitons, and it'd be nice to know if the interactions modify this formula significantly or not. I don't think they modify the entanglement part, but they might modify the area terms somehow in some interesting way. Yeah. Why it doesn't contribute? Yeah, so I can tell you in the photon why it doesn't contribute, which Guangdong I showed here. So basically, the edge mode contribution is some divergence. So there's some divergence, and you might have thought that there's some finite piece. So entanglement entropy typically has some divergent piece, and it can have some finite piece, and then it can have some pieces that go to zero as you take the cutoff to zero. And it turns out that the edge modes in excited states, they don't have a finite piece. So they have a divergent piece in any state, and they have some, which is universal to any state, and then they have terms that vanish as you take the cutoff to zero. And there's no finite piece. So that's what Guangdong and I showed. So because the divergent piece is universal, when you subtract off the vacuum, you kill that divergent piece. And then there's no finite piece, so you get all the pieces that go to zero as you take the cutoff to zero. And so you just get zero. That's basically the reason. It's like, the question is there a finite contribution in excited states to this S edge? And we showed that there isn't. And that's why it vanishes. But for gravitons, yeah, you need to construct these edge modes for gravitons. Turns out to be much more non-trivial. So I don't yet know how to actually show this for gravitons. The delta S is zero, but I think it's true. I think probably the same argument holds.
Can you go to that slide where you were looking at the polar cap and the delta rho the theta was small.
Yeah.
If you were able to take the approximation that delta rho would be small for the modular Hamiltonian approximation.
In the CFT?
Yeah, in the CFT side.
Yeah, here.
Yeah,
Here? Yeah.
So what does small theta 0 correspond to on the bulk side? Sort of like
on the bulk side, it's not as explicit. It's on the bulk side,
like a small excitation.
it's the fact that I wrote the entanglement entropy. Here I just went to order delta rho squared. So in principle, there's all the higher orders in delta rho, and they're all higher order in theta naught. So you could compute them, but they would just give higher order contribution.
In that case, is it possible to choose, let's say, not doing about zero, but doing about some non-trivial theta naught? So where you put up about some non-trivial theta naught instead of looking at small value about zero. So I don't know why that would be important.
Wait, if you mean around, sorry, can you?
So around so here you were looking at theta about zero, right? So let's say
Yeah. Oh, you mean like at some other
I'm
point?
just saying, yes,
Oh, yeah, I think by rotation symmetry, you can do any other theta. I think it would work, yeah.
Again.
Mhm.